Hello, everybody. Thank you for coming to this last session. I'm Sherry Mizumori, and I have the great honor to introduce our final speaker of this amazing meeting. Speaking of amazing meetings, I want to have my shot at being able to give Mike and Manuela Yasa a huge round of applause for really, you have put together this most impressively impactful anniversary meeting by bringing together some of the best minds that have contributed to our current understanding of the neurobiology of learning and memory. And for that, I'm very grateful. You have set the bar very high for future meetings, not only here, but elsewhere as well. And also thank you for asking me to introduce someone that I've admired for decades. Her work draws broadly on neuroscience to make predictions about cognition, as opposed to the other way around. And her predictions are tested using a combination of fMRI, clever behavioral paradigms, pharmacological studies, as well as patient studies, all in humans. And a particular interest has been brain systems that integrate different forms of learning and memory. Now, back when she was an assistant professor at Columbia, she was one of the few cognitive neuroscientists studying the nature of the interactions between different learning systems. The hippocampus and striatum were the two that a lot of the people were studying at the time. And she was doing it in a manner that paralleled animal learning and memory studies. And in the animal memory field, as many of you recall, this was back in the early 2000s, the nature of memory systems interactions was a hot topic of debate and discussion. And so when I became department chair, I seized upon this opportunity, and this would have been in 2012, to invite her to visit the University of Washington to give a prestigious public lecture on brain and memory. And of course, she gave an amazing lecture. But you may think I'm a little bit biased because her work is so relevant to my own work. So it's worth noting that just last week, we had our 2023 public lecture. And there, I was talking to some of our regulars, our community members who come often. And I spoke to this one gentleman, and this is now 11 years after our speaker came to the UW. And I asked him, what was your most memorable lecture of over the decades? I mean, he has been coming a long time. And he quickly said, it's the one about memory. He's a CEO of an entertainment, in the entertainment world, so he didn't know much about the brain. He learned a lot about the brain and was totally engaged with her presentation about why we forget. In fact, he said he continues to use this information in his own life to help him to remember. And so that's the kind of impact that one can have. Very impressive. Another strong memory for me from her visit was that she flew into Seattle, so I'm at University of Washington in Seattle, and she was in New York. And so she flew in the morning. She gave an evening public lecture, and then she took a red eye and went right back to New York to accept, on the next day, an award, one of her many awards. This one was the Lindfest Distinguished Faculty Award from Columbia University. So I thanked her for enduring such a crazy flight schedule from New York to Seattle, then back again, all in a short day. And then I remember her response, and it was, of course, she wouldn't miss an opportunity to connect with the public. And indeed, her passion to bring research to the community is still very strong. In fact, I think another facet of her research program aims to understand the developmental trajectory of multiple memory systems. And with this work, she has been working to improve the K-12 education and education policy by working with really frontline workers, the principals and the teachers and so on. Again, very, very impressive. And I think this is a powerful example of how we can bring our science to the community to impact important societal kinds of issues. And this is something I hope that we all are thinking about. Now, our speaker has extended her interdisciplinary systems level of research with truly innovative approaches and interpretations that help us to understand how sleep and motivation impacts memories and decisions, and what might go awry in memory and decision making with addiction, Parkinson's disease, and most recently, COVID-19. Also, recently she has used her research to better understand complex psychological constructs that previously might have been thought of as untouchable, such as the nature of creativity. Now, throughout her illustrious career, she's been recognized by almost every early and mid-career award that I can think of, too many to list here. But now she is, as a professor, she is now Kavli Professor of Brain Science at Columbia. And just this month, like not too long ago, she became the first woman to be appointed director and CEO of the infamous Zuckerman Institute at Columbia. So another thick glass ceiling was broken. So yay! So please join me in welcoming and congratulating Dr. Daphna Shohamy.
Hi, everyone. Thank you, Sherry, for that. I'm touched, and I'm also really frustrated that I'm not there to be talking with you and with everyone in person. I was so looking forward to this meeting and so looking forward to seeing so many beloved colleagues and students and people whom I haven't seen in a long time, and encountered just a complicated personal situation for any of you out there with kids with two parents traveling. I remember that trip that Sherry you were describing, and it's like 99% of the time, we managed to make it all work and get back. And I just encountered this situation where the only way to make it over to California would be to leave two teenagers alone at home, and I've seen too many bad movies to take that risk. So I ended up kind of stuck here in New York. That said, I'm really grateful both for the invitation to be part of this meeting, but also really, really grateful that the organizers were able to enable a distant lecture, despite the fact that it's far less satisfying not to be with you, and the last lecture of the conference, no less. So I'm just going to dive in. I know it's a strange thing to ask when I'm on a screen and you're in the audience, but maybe particularly for that reason, if something isn't coming through with either the sound or just the clarity or just kind of the lack of eye contact, please let me know. Maybe there's a way to kind of ask questions, or just raise your hand or let someone know so that I know you're listening, and so I can address any questions that come up. So what I'm going to be talking about today is a work we've been doing in the lab to try to understand the role of memory in decision making. And while I probably don't have to convince anyone in this particular audience of the importance of memory for really everything we do, I want to start from the angle of a lot of the work on decision making that's really undergone a transformation in the last 15 years or so. You've done a lot of work in neuroscience, systems neuroscience, and psychology and cognitive neuroscience to try to understand how we learn from experience to make good decisions. And I think it's really a striking area for kind of the cohesive and mounting evidence, all kind of shaping a particular framework. And that framework that's received an enormous amount of attention has suggested that the striatum is a key structure in supporting our ability to make good decisions that lead to good outcomes. On the screen here is just a smattering of a small number of studies. There have been many, many, many studies that have mostly highlighted the important role of dopamine and its inputs to the striatum in learning kind of the average value of candidate cues or actions. In learning that takes place incrementally, what we in the memory world would refer to historically as procedurally. And in many ways, most people have really thought of this as the basis of habits, kind of the neural circuits that supports habitual learning so that we can engage in actions and choices that will increase our likelihood of receiving a reward. And I know from the program that this is something that's been talked about. I've seen posters online at this conference as well. But of course, what's frustrated many of us in the field who think about behavior, both human behavior and animal behavior, is that most decisions don't work that way. This is a very elegant mechanism, although itself still has some work to sort things out, but that there are many other kind of cognitive mechanisms that play an important role in decision making. So here's a really great example, actually, because my understanding is this is the second Learning and Memory conference, and I was not at the first one. And so if we encounter this decision, as we all did, including myself, we don't really have a habit to lean on to say, yes, I should always go to Learning and Memory. And hopefully we don't have a habit that says, yes, I should always go to every single conference. Instead, what we have is maybe one memory from having done this once before, or maybe we actually have different kinds of rich representations and memories from other conferences, from things we know about the colleagues who are organizing and producing this, or other conferences we've been to in California. And so we know that these are the kind of rich representations, flexible representations that are provided by memory. But for a long time, we really didn't know how that kind of record, how that kind of knowledge impacts the decisions we make and what are the neural mechanisms. We know a lot more about that now. And we know now that there's a circuit in the hippocampus that provides this kind of information about a specific sample, an episode, something that happens once that we can use to guide decisions. And that this kind of circuitry coming from the hippocampus and its representations is also particularly well suited for guiding flexible decisions, for helping us make decisions that are not identical to ones we've made before, that have not been able to produce a habit. And I think a lot of the work in the last decade or so has suggested that the hippocampus, in fact, instead of working almost antagonistically with the striatum as we once thought, and instead of working independently of the striatum, that the hippocampus can work cooperatively with the striatum and can sort of provide this kind of input to the striatum as it calculates the expected value of various actions and cues. Here, I want to emphasize that I think in our hands and in the hands of many others, the idea here is really that the hippocampus is doing this often implicitly, not necessarily, but often, that these sort of rich relational representations from the hippocampus are automatically provided for the sake of decision-making. And of course, the most influential theory behind this view comes from Cohen and Eichenbaum, and the idea that the hippocampus binds elements of an experience across time and space. And this idea of relational memory for me and for my lab has been heavily influential, and for many of us, because if we think of memory as sort of a binding mechanism and as the outcome of memory encoding as a relational representation, that offers all kinds of new predictions and new ways of thinking about predicting rewards and making decisions for reward. So work in my lab has kind of tackled this from a number of different perspectives. We've done a lot of work looking at, especially in the last several years, at how individual episodes or kind of memory for one-shot events guides decision-making, even when it doesn't have to, even when we do have habits. We've done a lot of work looking at flexibility and how we can generalize from experiences we've had to new ones, and the role of the hippocampus in that. And most recently, we've become really interested in this notion of referring to loosely here as deliberation, as the decision-making process itself, and the ways in which memory might be shaping the way we think about the options and decide between them when there's no obvious better option to choose. And so today what I want to tell you about are two relatively new studies in that general space of deliberation. And a lot of the other work we've been doing over the past decade and a half or two has been summarized in a review paper spearheaded by Natalie Biederman in the lab and Akram Bakour, a former postdoc who's now at University of Chicago. So I want to kind of start by bringing us all back to what has been really the kind of cornerstone, a lot of the work in neuroscience and psychology on decision-making, right? So this is just a very simple moment. You're facing two options and you have to choose between them. And you have all kinds of maybe biases or information. A lot of the work on decision-making has focused on the idea that you have some kind of history with either this blue square or a green circle, or you're about to acquire that history and learn that one of them is usually more rewarded than the other. And we know we can track in the brain what happens as you're acquiring that information and as you're using that information. So what I want to talk today about is what happens when you don't have that information, or at least when that information is not clear-cut. So I'm first going to take you through an example of what you might think of as indecision, or when value information is not available to distinguish between the two options, and yet you still can and do choose between them. And then I want to take you through another new study that's looking at counterfactual valuation. What happens and what is the role of memory in figuring out when you do make a decision and later you learn something about the outcome, not just of what you chose, but of what you didn't choose. And I want to start with this very real world decision. And maybe I'm going to try this despite it's sort of crazy maybe to do it online, but I'm going to ask you to make a decision between Kit Kat and M&Ms. And if you would like the Kit Kat, raise your left hand. And if you'd like the M&Ms, raise your right hand. Great. Thank you. Oh, somebody really took a long time there. So what was really notable to me is not, whether the room in general prefers one or the other, but kind of that trickling of hands, which actually, thanks to the cameras, I'm viewing you all from the back. And so you can really see how the timing of your decisions varied quite a bit, with one person who seemed particularly undecided and need a little more time than others. And so for me, these are two of my kind of favorite chocolate bars. And so this is not an easy decision for me, even though it's a trivial one, right? It doesn't really matter. But because I like them equally, it takes me more time. And there's a lot of research that shows that we can probably infer your preferences between them based on the timing of your response. And so it's a very well-known phenomenon that when we're choosing between things that we like equally, we slow down. It takes us substantially more time. This is one of the most robust phenomena in human behavior and in animal behavior, that choosing between two things that are valued similarly takes more time. And I think this is, really, really puzzling. And I'm not the only one. This is something that the economists have found puzzling and philosophers have found puzzling, because we don't really get stuck. In fact, there's a kind of a paradox referred to in philosophy as Buridan's paradox that asks, what happens if a donkey is placed that was equally thirsty and equally hungry is placed in the same distance from something to eat and something to drink? And the paradox suggests that if preference guides our decisions, then that donkey should just be stuck and would eventually starve. Of course, we don't starve, and even I can choose between Kit Kats and M&Ms. And so we got very, very interested in thinking about how that happens. And maybe that this is one of the kind of behaviors where memory might play kind of a sneaky role in helping us reason through the options. So the big picture question here is, why do some decisions take more time than others? And the kind of big picture hypothesis that we got interested in is that maybe that time is going to producing evidence, just like figuring out what's happening around us takes more time when things are less discriminable, then maybe figuring out what we want based on internal evidence takes more time, because we use memory mechanisms like retrieval and prospection to compare the options to generate the evidence. And the kind of overarching interest in this area was really developed collaboratively with Akram Bakur, whom I mentioned is a former postdoc, now PI University of Chicago, or anyone looking for a great lab to join as a graduate student or a postdoc, and in collaboration with Mike Shadlin and Ariel Zilberberg, who were at Columbia at the time. Mike is still at Columbia, and has done a lot of work on perceptual decision making. And together we kind of tried to formalize what it might look like for memory to play a role in this kind of decision. And the idea was that for decisions based on internal evidence, the hippocampus may supply the evidence. And the more difficult decisions require more evidence and therefore more time. So the prediction, really straightforward then, would be that longer decisions may engage the hippocampus more. And this is a hypothesis we sought to test in a couple of different ways, which I'm going to walk you through. So the task that Akram designed looks something like this. First, we had people make this value-based task. So they had to choose between different kinds of snacks that were paired up in a way where we took advantage of knowing in advance information about how much people liked each of the individual items, so that we can construct pairs that were either easy by putting together an item that people liked a lot with something that liked a lot less, versus pairs that were going to be very difficult because they are two items that are valued similarly. For controlling for decisions in general and for visual input and so forth, we also had the exact same participants perform this perceptual task, where they had to determine whether there were more blue dots on the screen or more yellow dots on the screen. These moving dots that hopefully you can see coming through clearly. And what we did is we compared reaction time for the food choices, controlling for reaction time and decisions in general. So kind of using the perceptual task as a control. So first, let me just show you behavior. So what you see here on the x-axis, and I just ask you, can you raise your hand if you can see my cursor when I'm moving it and pointing here? Great, thank you. So on the x-axis here, we have the value difference between the two options. So here's right at the 0 is that point of indifference. So these are those notoriously difficult decisions. And the behavior I'm going to show you on the top is the probability of choosing the item on the right. So you can see here that people make choices that are consistent with their preferences the way we'd expect. This is in some sense a form of accuracy in the sense that the decisions are reflecting the reported value for the individual items. And you can see that the choices are noisiest at this point of indecision, as has been shown many times before and as we'd expect. And on the bottom here, I'm going to show you the reaction time. And we see here a very kind of classic effect, the one I was just describing. See this inverted U-shaped curve where people are slowest and noisiest at this point of indifference. The black lines here are the fits of drift diffusion models, which are very commonly applied to these kind of data and can describe choices as a function of reaction time and reconcile them. In the perceptual decisions, we see basically the same pattern, again, replicating many studies before us. People are accurate, and people show this classic inverted U-shaped curve. So it takes more time to decide between options that are closer in value, and we wanted to understand why that is. So I'm going to give you kind of an intuition for what we were looking for in an fMRI analysis. The first thing we were interested in is time, right? So we wanted to compare the reaction time regressors between the two tasks, just look at what happens in the brain when you're making a decision that accounts for the timing of a decision about value. We think of as internal evidence and preferences versus external evidence, like in the perceptual task. And we wanted to compare those two, but we also, of course, are interested in kind of capturing something related to memory. We deliberately use stimuli where memory should not a priori be a factor, and we're interested in whether we can find any evidence that memory is actually contributing to the decision, despite the fact that it's not a memory test in any explicit way. And so we had all participants undergo a separate kind of memory retrieval localizer. And with the fMRI analysis, we did a conjunction of this RT comparison with a regressor for memory retrieval, which was tested separately. And so that's this conjunction for this memory test on objects. I'm going to show you just one result from this study today. So in order to move on to some patient data, but basically what we find is this conjunction of reaction time, value greater than perception, and memory retrieval yields a significant effect in the hippocampus. In fact, it's pretty much a bilateral effect, just a little weaker here, and suggests that memory-related regions are more active with longer reaction times, especially for these value-based decisions. We did some connectivity analyses that kind of spoke to the network and addressing some of the questions that Sherry alluded to, kind of which parts of the brain are working with the hippocampus here, including the striatum, where we find interesting evidence for connectivity. But one of the questions on our mind and the data I really wanted to share with you today were, this is fMRI. And so it's interesting to see this kind of very specific effect manifesting in changes in bold activity in the hippocampus. But this is in many ways really not the kind of behavior that we all grew up on when we think of patients like HM or when we think of kind of typical people with hippocampal damage. And we thought that if the hippocampus is really important for this kind of behavior, then it would be critical that we demonstrate that in a patient model, that we be able to show alterations in these kind of decisions that take time in patients with damage to the hippocampus. So what we really wanted to ask is the hippocampus necessary for this kind of decision-making? And if you go through the research really carefully, which we've done in the lab, there are kind of hints of various reward-based behaviors that aren't exactly memory behaviors that are altered in HM and in other patients with hippocampal amnesia. But what you also see, there's actually very little data out there in patients with amnesia that report reaction time differences, and even less that has looked at decision time. So we had our work cut out for us, and we wanted to basically take the same task we had just used, but bring it to test with amnesic patients. So we had the great pleasure on collaborating on this project with Mika Verfai from Boston, Daniela Palumbo, who's now at UBC, and worked together to develop a task that could be friendly for patients with medial temporal lobe amnesia to try to get at this question. And so what I'm showing you here are the demographics of 6 amnesics with verified medial temporal lobe damage and classic kind of anterograde amnesia, and healthy controls that are matched in age and education and IQ. I'm going to show you the data from the hippocampal patients. We used a value-based decision task. I'll say we used somewhat different food items, whereas the Kit Kats and M&Ms were great for the undergraduates who were participating in the fMRI scanner. For the amnesics, we wanted to use stimuli that required less recognition. So we used things more like apples and sandwiches. And for all of the foods that we included in the study, they were the same foods included in the control study. And we verified in advance that everybody recognized the foods equally, amnesics and controls. And so here I'm just showing you this new group of controls matched to the patients, their behavior, which looks just like the controls from before. So you see, again, this sort of accuracy on top for the value-based decisions, and then this inverted U shape of reaction time on the bottom, and similar for the perceptual decision. And here are the data from the amnesics in red. So first you look at I'm showing you first the perceptual decision task. And as you can see, and as we'd expect, the amnesics are performing similarly to the healthy controls in terms of their accuracy and determining are there more blue or yellow dots, as we expect. Actually, somewhat surprisingly, saw that reaction times among the amnesics were, if anything, a little bit faster, not significantly so, but definitely not slower. And here's what we saw for the reaction time on the value-based decision. We see that accuracy is still high. They're able to perform the task a little bit noisier than controls, but we see this really striking slowing down of the reaction times in this value-based decision task when they have to choose between two equally familiar food items, and that effect is particularly pronounced at this point of similar values. So there's a real flattening of the curve and a real slowdown, both things, suggesting that hippocampal damage selectively impairs value-based decisions, not perceptual decisions. Oh, sorry, and those are the individual data here, just to show those for each of the 6 patients. You can see this is really kind of something we see in each and every one of the amnesic patients. So far I've shown you that difficult decisions take more time and involve hippocampal memory mechanisms. And we think that this could be related to the deliberation and to the process that's required to sort of construct value when we have to choose between things when we don't have knowledge of the value before us. And one of the questions that we got interested in the lab then is like, well, what are the consequences of that? If you're facing a decision and you're engaging memory mechanisms to reach the decision, what are the consequences for what happens after that decision is made? And that is a direction that Natalie Biederman, a graduate student in the lab, got very interested in, partly based on personal anecdotes of difficulty in deciding between equal value items, and partly based on kind of noticing a really interesting gap in the literature. And essentially what we realize is that while when you sort of look at this kind of decision between a blue square and a green circle, that the decision-making people and decision-making process really requires that you separate those options, right? Especially if they're similar in value, what you're looking for is evidence to distinguish between them. You have to make a decision to tease them apart. And in fact, the word to decide comes from Latin, and from decide, which means to kill off. So basically, we know that to make a decision, you have to kind of, remove an option. But when we think about this from a relational memory perspective and as memory researchers, we also know these are two events that are co-occurring in time and space, and that this is exactly the kind of exposure and learning that leads to the binding of associations together. So we got interested in the consequences of both of these processes happening at once. And we reasoned that perhaps because of this binding effect, choice options that you need to decide between actually become associated between them in memory. And that for that reason, later learning about the chosen option can elicit reactivation and updating of the unchosen option, but in this case, in the opposite direction. And the intuition behind this, I think, is really best captured by a scene in the movie Inside Out. So I don't know how many of you saw the movie Inside Out, but you're sort of exposed to the inner thinking of the characters. And there's a moment where the mother is pissed off with the father, and they're fighting. She's annoyed, and as she's feeling angry with her husband, they sort of display in her mind that she's thinking back to this Brazilian pilot that she could have married but decided not to. So sort of think about this as an example of how when an outcome of a choice is either unusually satisfying or unsatisfying, that you reactivate in memory what the other option could have been. So we wanted to test this and not just rely on Pixar animations. And so Natalie designed this task that has 3 phases. There's a deliberation phase, an outcome phase, and a decision phase. And in the deliberation phase, people choose between 2 options that are similar in value based on pre-testing. So they go for the blue, and here for the pink. And then in the outcome phase, we tell them what their choice yielded, right? So in this case, the choice of the blue square yielded $2. The choice of the pink star yielded no reward, 0. And then we ask them to make decisions between the options that they never learned anything about. So the green circle and the orange cone. And so technically speaking and rationally speaking, there's really no difference between them. They should be guessing between them. But the question is, did they sort of apply what they know about the fact that this one was rewarded and this one wasn't, to think maybe this was the better choice here, or maybe this was the worst choice here? And I just want to point out, I'm not sure who's in the room, but there's sort of some critical differences here in the design between a sensory preconditioning paradigm that we and others have used, and the prediction here is really the opposite. And so just point that out. The key process here is that there's a decision to be made, that while there's a binding putatively, there is also a separating. And that, I think, is one of really the key differences here. We designed this, Natalie designed this using these paintings where she got people's advances pre-rated, and these are kind of the actual stimuli used in the task. These are stimuli that were complex, where it wasn't sort of obvious which one was high value, low value, and we had a cover story of sort of an auction. So all the stimuli were pre-rated and chosen for being neutral so that we could encourage people to really deliberate carefully when they're making their decision early on. And we asked then, does learning about the chosen option modulate the inferred value of the unchosen option? And the idea was that we thought that memory for this binding, so the strength of the associative memory between the 2 options during the deliberation phase, should be predictive of the extent to which people choose the alternative option in the test phase. So I'm going to show you some behavioral results, and if I get to it, some modeling. So first I'm showing you here what people chose. So on the left here are the chosen options, and on the right are the unchosen options. And I want to walk you through kind of some of the reasoning we had first. So we expected people to be really good at the chosen options. There's no reason why they wouldn't be. This is a really simple task. You find that something was rewarded or you didn't. But there were 3 different ways to think about what might happen in the unchosen option. One is, again, rationally speaking, that they would just be a chance here. They'd be equally likely to choose the one on the left or the one on the right. The second would be that actually they might attribute the outcome that they experienced equally to the thing they could have chosen, right? That there'd be sort of some more synergistic generalization that if one option was good, then the other option would have been good too. And then the third option was the one that reflects the hypothesis we walked in with, was that actually we see the inverse effect, that people would be less likely to choose whichever item was associated with an option that got rewarded later. So here's the actual data from the first study we ran. And as you can see, on average, we found that people were very good at choosing the rewarded option, and that people showed this sort of consistent bias against choosing the unchosen option if its counterpart was rewarded. And here's the within subject data. We're plotting memory accuracy on the x-axis and the inverse decision bias, as we're calling it, on the y-axis. And you can see that there's a positive correlation. So the more accurate people's memory was on a straight associative memory test for the memory for the pair when they made the decision, the more likely they were to show this effect of biasing their decision in the opposite direction. So choices reflect an inverse decision bias that's correlated with associative memory, both across and within participants. So the inverse decision bias that Natalie uncovered with this paradigm shows that there's a tendency to infer the value of the unchosen option in opposition to the chosen. I think this really adds to many other studies showing how structured or modeled understanding of the world based on memory can be very important for guiding decisions that are not straight habitual decisions, but that require some understanding of an associative structure across stimuli. And here we show specifically that this effect is highly variable, but that variability is in part explained by a correlation with memory for the original choice pair. So very specifically a role for memory in this process. And just to mention, this data was pre-registered and replicated across 5 data sets, and it's robust to changes in reward, the stimuli, and the repetition. Finally, when we ask people to just do an explicit value estimation, like how much do you think this particular stimulus is worth, we see the exact same kind of bias in value. So in the last few minutes, I wanted to show you some data we have trying to address whether memory plays a causal role in this process, and to try to link this inverse bias to some models of value-based decisions, and particularly to something called the policy gradient model. And this work on memory, sort of follow-up work on memory and a policy gradient model, we did in collaboration with Sam Gershman from Harvard. And the first thing we did is say, to be really convinced that this is memory and that we should be taking the memory results seriously, we want to show that changes to memory that we can introduce in the task should have an effect not just on memory, but also on this decision pattern that we found. So we went to kind of a classic manipulation of retroactive interference, where we pair old items with new ones and show that that reduces later memory. And predicted that we'd find reduced memory, we replicate these classic results, and that we'd also find a reduced inverse bias, so that this memory manipulation, if memory is playing kind of a really important role in inverse bias, should be modulated by this effect. And that moreover, despite kind of reducing the bias overall, we'd still expect to find that memory correlates with the inverse bias if it's playing an important role. So we took the task design and basically doubled all the stimuli up and introduced a memory interference in between the decision-making and the outcome learning, where half of the stimuli were now paired with new stimuli, and we'd expect that that would reduce memory. And then we can test the effect on the inverse bias. So we wanted to ask, does retroactive interference reduce both the memory and the inverse decision bias? So here's the memory accuracy as we expect. Sorry, let me pull up the legend here. So the baseline condition, like in the first study, is in green, and the interference, the retroactive interference effect, in orange. So we find that memory accuracy is significantly lower when we introduce this retroactive interference. And when we look at the choices, we find that the interference has no effect on memory for the chosen options, but it does soften, reduce this inverse bias effect in the interference condition relative to the baseline condition. Nonetheless, when we look at the individual differences, we see that within individuals, the accuracy of the memory and the inverse decision bias holds and replicates from the previous study. So it suggests that retroactive interference reduces memory and reduces the inverse decision bias, while the relationship between them remains the same. So some conclusions. And did I take out the, I did, I took out the modeling. I was worried about time, but I was actually accurately worried about time. So let me just state them as I go through the conclusions here. So it shows us there's a role for the hippocampus in guiding decisions that depend on internal evidence. I think this has really interesting implications for models of memory, thinking about how this inverse bias comes to be. And Natalie is now working on the fMRI version of the study to see, can we track when and how neural circuits are recruited to change the value of options that were never directly paired with reward or lack of reward. And this also has all kinds of implications for models of decision-making. I mentioned the policy gradient models. It turns out that these policy gradient models explain value-based behavior in a way that's complementary and orthogonal to the classic reinforcement learning models that assume kind of a gradual learning of reward value. But nobody's really talked about where that policy comes from in the policy gradient work. And so what we reasoned and what we argued in this paper that's now in press is that I think there's now lots of evidence, ours included, that suggests that the policy might, at least in some cases, come from hippocampal relational memory mechanisms that offer associative structure that can be used with these policy gradient models in addition to what's already been shown for some of the model-based reinforcement learning mechanisms. So I'll end there. Thank the folks in the lab, Natalie here, Akram, who spearheaded the first study, and Sam Gershman, who collaborated with us on that third study. I want to thank you all for sitting through a Zoom talk. I haven't given a Zoom talk in a very long time, and I hope this is not going to be a frequent occurrence, but I've been really grateful to be able to connect with you nonetheless.